morning children. In the previous video, we learned how to derive an expression for the work done during an irreversible compression of the gas. Irreversible compression of the gas. We had learned that we had taken one cylinder, and in the cylinder there used to be one piston here in the initial stage. This is the volume initially brought, and after compression, the piston reaches to the final volume. And as the final volume is less than the initial volume, we got the work done as P external into the V final minus V initial. This is the derivation that we had derived in the last session. But now in this session we are going to see derive an expression for work done in a reversible expansion of the gas. Reversible means already in the container some gas is there, but when you supply some amount of heat, this gas will be expanding. What is happening for this gas, children? The gas will be expanding. See now, the piston which used to be at this location initially, now this was its final location. It was its final location. The gas is expanding. Generally this was used in running the steam engines. Expansion of the gas used to move the engine front and back. So how to derive the work done in such case? Now in such case, the expansion of the gas will not take like a bursting. It will take very slowly with small change in the volume of the given ideal gas. Right. So during this expansion of the gas, the small change in volume during the expansion of gas, the small change in volume is given as the small change in volume. It is given with the symbol small dV. Here whenever we is giving the small d, it is showing that there is a small change in the volume. There is a small change. Wherever you bring the small d, it indicates that there is a small change in the volume from its initial stage. Now here, the external pressure that we are applying, it is getting overcome, or the external pressure is getting less. In shortcut, we can say the external pressure in this case, it is getting small deviated from its exact position. Means some pressure it is experiencing from inside. So this external pressure, we are saying it is obtained by removing small change in the pressure from the internal pressure. How do you express the external pressure here, children? By subtracting small change in the pressure from the internal pressure. So that is useful in deriving the next step. So let us see how we had given the work done previously. We had given the work done in this method in the last class. Or we can also give this one as W is equal to minus P external pressure into delta V. We can give in the method we had given in the last class. But now let us see here to find work done during the reversible expansion. Small work is done. That is assumed. Small work is done. That is minus of P external pressure into with the small change in volume. This in the place of delta V and bringing as dV means there is a small change in the volume. What is there? There is a small change in volume because the piston was moved forward. From the initial position. Means the volume is not going suddenly increase. It is just going a slight increase as the work is done by the system. The gas is expanding. It will not expand at a time. There is small change in the volume. So how is the work done? We are giving work done is equal to minus P external pressure into small change in the volume. But how to get this external pressure? We already came to know. It is obtained by subtracting the small change in the pressure from the internal pressure. So we are substituting the formula there. The work done is given as, in the place of P external pressure we can write as the P internal pressure minus small change in the pressure into D. Or now we can write P internal pressure into dV plus dP into dV. What is meant by dP? Small change in the pressure. Small pressure change. And dV means small volume change. As the change is very small, this part can be neglected or negligible. In order to remove this part, we are making it very less, so it is negligible. So finally, what we can write, delta W is equal to minus P internal into dV. In order to get our work done in the logarithm form or the natural logarithm form, we must integrate this equation on both sides. What we must do? Integrate this equation on both sides. So integrating on both sides. Integrating to get final work done. How we are bringing integration of the small change in the work done is equal to minus of integration of V1 to V2. Where are the limits from? Initial volume to final volume into P internal pressure into small change in the volume. But what do we know about ideal gas? For ideal gas, we know P is equal to nRT upon V. So this P is nothing but the pressure of the gas. So we are making our equation like, already this integration and small change in the volume are cancelled. So we are bringing W is equal to minus of in the place of P internal, I am adding this one as the nRT of integrating V1 to V2 dV upon V. Or you can speak, this is the small change in volume. That's what you can say as V2, and this is as the initial volume. Or we can write this equation as W is equal to, if you remove the integration, you will get that in the form of natural log, and D, you will get that one in the form of natural logarithm. The natural logarithm is in the form of minus 2.303 log base 10. Don't forget, this is called natural logarithm form, and the next one is called log base 10 form. This is the log base 10 form. So these two values you must not forget. So upon remove the integration, you will get this one as the minus nRT ln V2 minus V1. That is the change in the volume, final volume. V means the initial volume. So if you want to remove this ln, it is equal to minus 2.303 log base 10. So we are writing our work done as work done is equal to minus 2.303 nRT log base 10 to V2 minus V1. So this is the formula that we will use to do the work done. But what we know according to Boyle's law? volume is inversely proportional to pressure. Volume is inversely proportional to pressure. So you can express this equation in the same form with respect to pressure as W work done is equal to minus 2.303 nRT log base 10 V2 upon V1. In the place of volume is inversely proportional to pressure, no? So you can write difference that P1 upon P2. P1 upon P2. So these are the two derivations that we can use for work done regarding the reversible expansion of the gas. So let us continue here. How about the derivations that we have done now? We have done the work done regarding irreversible expansion of gas. What is the equation for this irreversible expansion of gas? Work done is equal to minus of P external into final volume upon initial volume. That's what we can also take V2 by V1. Sorry, final volume minus initial volume. That is delta V. We can write. And work done in a reversible expansion. Work done in a reversible expansion. P external is equal to how we got minus 2.303 nRT log base 10 V2 upon V1. These are the two derivations that we have derived under two similar different conditions. Two different conditions. One is a reversible and one is of the reversible. Generally, when you see the gas expands in vacuum, it is called as a free expansion. Expansion of a gas in vacuum. Expansion of a gas in vacuum is called as the free expansion of the gas. It is called as the free expansion of the gas. Here there will not be any work done. There will not be any work done. During the free expansion, work done will not be there. We are already learned about isothermal process. What is isothermal process? The constant temperature process. Constant temperature process is called as the isothermal process. But here we need to derive 2 points. Derivation, derived expression for work done, derived expression for work done. The first condition is isothermal reversible expansion of gas. Isothermal reversible expansion of the gas. Isothermal reversible expansion of the gas. Let me check the lighting once. Yeah, let us see, is the lighting sufficient? Not very good. There are expression for work done using isothermal reversible expansion of the gas. And one more here. How do we know about the internal energy? Delta U is equal to Q plus W. During the isothermal process, delta U will be equal to 0. What is the delta U value? Delta U will become 0. So we will give our equation as Q is equal to minus W. But during isothermal reversible expansion of gas, what is the equation we know? W is equal to minus 2.303 nRT log base 10 V2 upon V1. So here we can write it in the W value. So Q is equal to minus into 2.303 nRT log base 10 V2 upon V1. So this minus and minus will have a plus. So Q is equal to plus 2.303 nRT log base 10 V2 upon V1. So this is the derivation for the work done during isothermal reversible expansion of gas. So the same we can do the work done for isothermal irreversible expansion of gas. Isothermal irreversible expansion contraction of the gas. What is the isothermal state? Delta U is equal to Q plus W. Whenever isothermal is there, delta U will become 0. So Q is equal to minus W. Q is equal to, for irreversible process, what is the Q value? Minus P external into V final minus V initial. So minus P external into V of final minus V of initial. So we can write Q is equal to V external pressure into V final minus V initial, or we can write the same as V external into V2 minus V1. So these are the two derivations for the work done during an isothermal pre-expansion and irreversible and reversible process. Let us do two of the numericals now. Let us see here about one of the numerical problem. Where was there? Calculate the total work done. 1 mole of a gas expands. 1 mole of a gas expands isothermally and reversibly from an initial volume of 20 decimeter cube to final 40 decimeter cube at 298 Kelvin. The main thing is it a reversible or irreversible expansion? We need to say it is a reversible expansion of the gas they are saying. What is the work done formula we know for the reversible expansion of gas cement? W is equal to minus 2.303 nRT log V2 upon V1. Do you know the terms here? What is the N value? N value how much was given? 1 mole was given. What is the R value? 8.314 joule Kelvin inverse mole inverse was given. And temperature 298 Kelvin is the question given there. And what about the V2? V2 means final volume. V2 is the final volume. How much had they given? 40 cubic decimeter. And V1, that is called as the initial volume. It is given as the 20 cubic decimeter. So substituting these all values to be worked done, we get W is equal to minus 2.303 into N value 1 mole into R value 8.314 joule Kelvin inverse mole inverse into temperature 298 Kelvin into log 40 cubic decimeter upon 20 cubic decimeter. So I am casting this decimeter and decimeter cube, and 2 into 40 2 times. So what are the things we can remove? Children? Right? Good. Now 1 mole is equal to 1 mole there. Kelvin and Kelvin we can remove. Kelvin and inverse and Kelvin we can remove. So here work done, how much value you will be getting, you need to multiply this. But here one major thing you must not forget is into 1 into 8.314 joule mole inverse into 298 into log 2. Do you remember the log 2 value? 0.3010. How much is the log 2 value? 0.3010. So substitute this value and you get the some value, whatever is there, that is in the joule mole inverse. So do the calculation, children. and in this method you do the remaining problems. Thank you.